This video goes over sketching polynomial functions using their characteristics. So right here, both of these polynomial functions are in factored form. The first thing that we're going to do is identify the leading coefficient. In this case, it's a positive in front of the bracket, so our leading coefficient is positive. The next thing that we're going to identify is our degree. And so our degree is really how many x's there would be. Here we've got one x in each bracket. So if we multiplied those together, we'd get x squared. So then we have degree 2, which is even. Once we've identified those two things, then we can identify our end behaviors. Here we've got a positive even degree function, which means that both ends of the function are going up. Hopefully you're kind of recognizing that this is a parabola so that those end behaviors make sense. Now that we've identified the end behaviors, we are going to identify the x-intercepts, which is nice for us because it's in factored form. We have 2. We've got our first x-intercept, which is -1 and 0, comes from that first bracket. And then we have a second x-intercept that is at 3 and 0, comes from the second bracket. Remember, for those x-intercepts, we are just setting the function equal to 0 and solving. The maximum number of turning points, we'll call them TP for turning points. We know that that's the degree -1, so the maximum number of turning points is 1. And then we also need to identify the y-intercept. So for the y-intercept, we're going to set x equal to 0. And we're going to solve. So we have 0 plus 1 in the first bracket, which is 1. We've got 0 minus 3 in the second bracket, which is -3. So that means that f at 0, or our y-intercept, is going to be -3. I can write that in coordinate form like this. Now I'm going to use all that criteria to sketch the graph on the grid below. I'm going to start by plotting my x-intercepts. So -1 is probably right about here. +3, if I go over 1, 2, 3, we've got 3 on the right-hand side. I also have my y-intercept, so I'm going to go down 1, 2, -3, about right there. And then I know that my end behavior, both of the function ends go up like this. Those roots have multiplicity 1, so my function is just going to pass right through the x-axis. And then we're going to do the y-intercept, and then I'm going to connect my x-intercepts to get my function. We'll do the same thing on the second side. We're going to start by identifying the leading coefficient. I notice that there is a negative sign in front, so that means that my leading coefficient is negative. My degree, in this case, I've got 3 brackets that each have an x in them. When I expand that, I would get x cubed, which means the degree of my function is 3, which is odd. My end behaviors are then that of a negative odd function, which means they are finishing in opposite directions and they're going down to the right, just like the equation of a line with a negative slope. Our x-intercepts, we've got 3 this time. They each come from the brackets. We've got -2, 0, -5, 0, and then +4 and 0, just like we did with the quadratic, the degree 2 function in part A. Now we're going to identify our max number of turning points. We have a degree 3 function. The maximum number of turning points is the degree -1, which is 2. And then the last characteristic that we're going to find is our y-intercept. And we're going to set x equal to 0 to do that. So f at 0, I've got 0 plus 2, don't forget that negative sign, which is 2, 0 plus 5, which is 5, and then 0 minus 4, which is -4. Multiplying all of those together gives me my y-intercept of positive 40, which I can write in coordinate form like this. And those are the 4 points that I'm going to start with plotting on my grid to sketch my function. So I'll do the x-intercepts first. I've got -2, -5, positive 4, and then my y-intercept of positive 40. This is a sketch, which means that your points are just an estimate. They need to be correct relative to each other's location, but we don't have an explicit scale like we do in a graph. I know that the multiplicity of each of those roots is 1, which means at every point on the x-axis, it passes directly through. And I know that it's going down to the right. Okay, this tail is going up to the left. And I know that my maximum number of turning points is 2, which means it changes direction twice, which means that I'm going to go down, back up through this x-intercept, up through the y-intercept, and then change directions again to finish my shape of the graph. Example 2 asks us to identify the values of which f at x is equal to 0 in both cases. So for part A, the points where it's equal to 0, those are my x-intercepts. That line that I've drawn represents all of the y values, which means I'm looking for the part where that y value is equal to 0, the only place that is true on the x-intercept. So for part A, I would have, and I'm just going to represent these as a list of values. I'm going to say that x could be equal to -1 or 3. And then for the second function, I've got 3 values. So I've got -5, -2, or 4. So now the second part here asks me, well, I'll use green, for which values of x are going to be less than 0. So that means the part where the line, the blue line that I've drawn, is below the x-axis. In the first one, that is the scoop of the parabola. In the second one, there are 2 points here. There's the first little scoop in quadrant 3, and then there's the finishing part, or the end behavior, that is going down to infinity. So it's important to note that you're looking for when the function values are less than 0, not less than or equal to. So that means that I'm going to state the values for x that are just less than 0, which means for the parabola, they are in between -1 and 3. Remember, those open brackets mean not inclusive, so the endpoints aren't included in that range. And then in my second function, I have 2 values. I'm going to say that it is -5 and -2, as well as 4 all the way to infinity. Both of those intervals represent the green sections that I have highlighted on the graph. The last part here represents when they are above 0. I'm going to use purple for that one, so I like purple. Okay, so here I'm looking for when the function, we're just going to do greater than 0. I'm going to change that one there. Okay, when f at x is greater than 0, which means that I'm looking for the part that is above the x-axis on both sides. So the cubic function, I've got 2 parts. The quadratic function, I only have 1. So in the first one, my range is going to be all the way from -infinity to -1, the value of that first x-intercept. And it's also going to be from 3 to positive infinity, represents those x values that are above. And then in my second function, I also have 2 sections. I've got -infinity to -5, and then in between 2 and 4.